Today we'll discuss about rise time and the relation between rise time and bandwidth. So what is rise time? Rise time is denoted by T subscript R and is defined as the time taken by the signal to reach the final value from the initial value. How much time the system takes or the signal takes to reach from its initial value to the final value. That is called rise time. From the initial value till the final value, rise time. So let us derive a relation between rise time and system bandwidth. So to derive the relation between rise time and system bandwidth, I am considering my system to be a ideal low pass filter. This is my system. This low pass filter has cutoff frequency omega c, right? The ideal low pass filter has a cutoff frequency omega c, and at the input of the system I am applying a unit step function. So if I apply a unit step function to a low pass filter, how will my output look like? That we will find out, and then from there we will calculate the time taken for my output to reach its final value from its initial value, right? So first, let me calculate the impulse response of the ideal low pass filter. This we have already calculated in the previous slides. What is the impulse response of the ideal low pass filter? It is h of t equals to omega c divided by pi into sampling of omega c into t minus d. This is the impulse response of ideal low pass filter, right? Then we will find the response of the ideal filter for u of t. When the input is a unit step function, we will find the response of the ideal filter. How will we obtain the response of the system y of t? It is nothing but convolution of the input with the impulse response. So my y of t is nothing but u of t convolved with h of t. Right? Since it is commutative, I can write h of t convolved with u of t. Now I am writing the convolution integral. Integral minus infinite to infinite h of tau u of t minus tau d tau. Now let me substitute in place of h of tau in place of u of t minus tau. Now u of t minus tau, it is only defined for values of t minus tau greater than or equals to 0. So what does this mean? This means tau is less than or equals to t, right? That means tau is ranging from minus infinity to t. The maximum value tau can take is t. So my limits now become minus infinite to t h of tau d tau, right? H of tau d tau. Now in place of h of tau, I will substitute my h of my impulse response. In place of t, I will substitute tau and I will replace h of tau here. Now I will integrate this integral. So what will happen? Minus infinite to t omega c by pi integral sampling omega c tau minus d d tau, right? So omega c by tau by pi is constant, so I'll get it outside. And what is left? Integral of sampling function. Then omega c, this term inside the sampling, I am replacing it by a dummy variable s, right? I am replacing it by a dummy variable. Then if I differentiate this term with respect to tau, then what will I get? I'll get omega c into d tau. Omega c into d tau is equals to ds. That is what I'll get, right? When I differentiate with this with respect to tau, minus d into omega c becomes 0. Now omega c into d tau is equals to ds. From that I'll get d tau is equals to ds by omega c. And then I'll check my limits also. When tau is minus infinite, what happens to S? S is also minus infinite. When tau is equals to t, when tau is equals to t, S becomes omega c into t minus d, right? When tau is equal to minus infinite, my S is equals to minus infinite. When tau is equals to t, S is equals to omega c into t minus d. Now my new limits are minus infinite to omega c into t minus d. So let me substitute all of these in the previous expression. I'll get this equation. Now here omega c and omega c gets cancelled. I have 1 by pi integral of sampling function. Now integral of sampling function is a standard integral and it is called sine integral. It is called sine integral. Integral of a sampling function is sine integral. It is denoted by si of s. Okay, si of s, and it looks something like this. This is how my sine integral looks like. So the three important properties of sine integral are: at 0 the value is 0, at infinity the value is pi by 2, and at minus infinity the value is negative pi by 2. The sine integral is nothing but from 0 it increases, and then it kind of has damped oscillations, and at infinity it settles at pi by 2. Similarly, at minus infinity it settles at minus pi by 2. This is my sine integral. Now let me replace this integral sampling function with sine integral. So that is what I will get. I'll get this expression. Now if I substitute my limits here, I'll have omega c into sine integral of omega c into t minus t into 1 by pi, that is this term, minus sine integral of minus infinity. Sine integral of minus infinity is negative pi by 2. So minus into minus pi by 2 is plus pi by 2. And I have an amplitude that is 1 by pi. So 1 by pi into plus pi by 2. I have 1 by 2. So this is my final output. So how does this output look like? That is what we're going to see now. Okay. So first, this is nothing but a sine integral, a delayed sine integral, right? By how much is it delayed? It is delayed by d. It is delayed by d. So let me draw the same sine integral that is delayed by d times. I mean the time delay is d terms. So my sine integral is going to look like, so this is how my sine integral will look like. Previously this was the position of 0, right? Previously my position of 0 was here, right? This is the position of 0. Now it is delayed by d times. So since it is delayed by d times, whatever is there at 0 will now be at time d, right? It is not 0, it is time d. Then what is the amplitude here? The amplitude is going to be at amplitude, the final amplitude here is pi by 2, and here the final amplitude is going to be negative pi by 2. So if I multiply that with 1 by pi, right? 1 by pi is the amplitude of my sine term. So 1 by pi. What do I have? I have 1 by 2 on the 1 by 2 here, and I have negative 1 by 2 here. So I will erase all this and write just 1 by 2. Okay, I'll just write 1 by 2. 1 by 2 is my amplitude, and negative 1 by 2 is my other amplitude. Then I have a DC term of 1 by 2. So for the whole signal, I'm going to add 1 by 2. So what happens? This entire signal is going to shift upwards by how much? By 1 by 2. So when the entire signal shifts upward by 1 by 2, here my final amplitude is going to be 1 by minus 1 by 2 and plus 1 by 2. So final amplitude is going to be 0, and here it's going to be 1 by 2 plus 1 by 2, that is 1, right? And here it's going to be 0. So my x-axis will now be at this point. This is the x-axis. That is the x-axis. And let my y-axis be somewhere here, right? Somewhere here, because this is nothing but a delayed version of my original sine integral. Now this is d. This position is d. I'll calculate the position of my final amplitude, right? This is my final value here, and this is my initial value. I'll consider from this point till this point. From my initial value till my final value, how much time it is taking. That is what I have to find for rise time, right? What is rise time? Rise time is the time taken by the signal to reach its final value from its initial value. Now let me calculate the time limits here. Time limits here. So what is this? This is sine, right? Sine integral is nothing but this. It is equal to plus or minus n pi. So what is t? T is equal to d plus or minus n pi by omega c. So what is the value of t when I have my maximum amplitude? It is d plus pi by omega c, right? Because it's on the positive side of t, right side of d. So this is nothing but d plus pi by omega c. And when is my initial value occurring? My initial value occurs when n is equals to minus 1. So that is d minus pi by omega c, right? D minus pi by omega c. So this point I have what is the time value, and at this point also I have the time value. So what is my rise time? Rise time is the time taken for my signal to reach the final value from the initial value, right? That is from this point till this point, right? What is the difference between these two? So my rise time tr is equals to d plus pi by omega c minus d minus pi by omega c, right? D plus pi by omega c minus d minus pi by omega c. So d and d gets cancelled. I have 2 pi by omega c, right? My rise time is 2 pi by omega c. Now the bandwidth, we have considered a low pass filter, ideal low pass filter. We have considered an ideal low pass filter. So what is my bandwidth? My ideal low pass filter was minus omega c to plus omega c. This is the cutoff frequency of my ideal low pass filter, right? So the entire, and what is the bandwidth here? Bandwidth is going to be the system bandwidth is going to be how much? It is going to be omega 2 minus, sorry, this is omega 2, yeah, okay, omega 2 minus omega 1. So omega c minus omega c, that is 2 omega c. So now my TR is going to be 2 pi divided by omega c is nothing but b by 2, right? Omega c is nothing but, sorry, my bandwidth is going to be, now my bandwidth is going to be omega c divided by 2 pi, right? That is nothing but fc, right? This is my bandwidth. Now if I substitute that here, tr is equals to 2 pi divided by here I have omega c divided by 2 pi, that is into 2 pi. So this is nothing but 1 by b. This is nothing but 1 by b. So what is the relation between rise time and system bandwidth? It is rise time is equals to 1 by b, right? Rise time is equals to 1 by b. So this is the relation between rise time and system bandwidth in case of a ideal filter, in case of a ideal low pass filter, right? Now we'll look for the rise time in case of a practical low pass filter. In case of a practical low pass filter, we will look. So what is a practical low pass filter? A practical low pass filter is nothing but a simple RC low pass circuit, right? RC circuit. This is my practical low pass filter. So for this I will find the impulse response. We have already calculated this previously. Previous slides we have already calculated, right? So this is my impulse response for the practical RC filter. H of t is equals to 1 by RC e power minus t by RC into u of t. Now assuming I am applying the input as a unit step, my unit step I am applying as a input to the filter, what will be my output, right? Now it's going to be convolution of h of t and u of t, right? Convolution of h of t and u of t. Now when I apply in unit step function to a system, then what will the response be? The response is same as step response, that is denoted by s of t. We have studied this in properties of LTI systems. So what is my step response? It is given by integral negative infinity to t h of tau d tau. Okay. Now in place of h of tau, I am going to substitute my impulse response. Okay. Then since I have u of tau here, u of tau is defined for tau greater than or equal to 0. So tau is now the lower limit of tau is now 0. It is made 0. 1 by RC is a constant, so I'm getting it outside. Now I have to integrate this term. So when I integrate that term, what will I get? I'll get e power minus tau by RC divided by minus 1 by RC, right? So this term gets cancelled and I have a negative sign there. And if I substitute the limits here, I'll get e power minus t by RC minus e power 0 is 1, right? I have a negative sign here and I have e power minus t by RC minus e power 0, that is 1. So if I get this negative sign inside, I'll get 1 minus e power minus t by RC. This is my y of t. Right? This is my y of t. Now, rise time we have defined as the time taken by a signal to reach its final value from initial value. That is in case of ideal systems, only for ideal systems. Now, in case of practical systems, we define rise time as the time taken by the output or the signal to reach 90% of its final value from 10% of its final value. If the final value, let us say it is 1, if the final value is 1, then for the signal to reach 0.9 from 10% of its final value, that is from 0.1. From 0.1 till 0.9, how much time the signal takes to reach 0.9 from 0.1 is the rise time in case of a practical system. So now we will consider our output signal at 10% of its final value, right? The final value is 1, 10% of final value is going to be 0.1, right? So my final value, my y of t is the final value, that is 0.1 equals to 1 minus e power minus, in place of t I am writing t subscript 10, okay, t10, that denotes the time at 10% of its final value divided by RC. Now I'll take this, I'll take my exponential term to the left side and my constant terms to the right side. Now what do I have? I have 0.9 equals to e power minus t10 by RC. Now I'll take natural logarithm on both sides. So ln of 0.9 equals to negative t10 by RC. ln and e gets cancelled. So I have negative t10 by RC. So what is my t10? t10 is going to be minus RC into ln of 0.9. So if I calculate the value of ln 0.9, I'll get t10 equals to 1 t10 equals to 0.105 RC, right? This is the time. This is the time at 10% of the final value. Similarly, I'm going to calculate the time at 90% of the final value, right? 90% of the final value is 0.9. So if I substitute and calculate, I'll get T90 is equals to 2.32 RC. This is the value. This is the time at 90% of the final value. So my TR is now what? T90 minus T10, right? T90 minus T10, 2.32 RC minus 0.105 RC. That is nothing but 2.2 RC. This is my TR. Now band cutoff frequency for a low pass filter, so low pass RC circuit, what is the cutoff frequency? Cutoff frequency equals to FC is equals to 1 by 2 pi RC, right? This is my cutoff frequency. Omega C is generally equal to 1 by RC, right? That means FC equals to 1 by 2 pi RC. This is in case of a practical RC low pass filter. Now I'll substitute in place of RC, what can I substitute? I can substitute 1 by 2 pi FC, right? 1 by 2 pi FC. So FC is nothing but my bandwidth, right? Fc is nothing but my bandwidth. We have seen in the ideal case. Now 2.2 divided by 2 pi is nothing but 0.35. So my TR is equals to 0.35 divided by B. This is the rise time in case of a practical low pass filter. In case of an ideal low pass filter, it was 1 by B, right? In case of practical low pass filter, it is 0.35 by B. So this is the relation between rise time and system bandwidth.